soda with this full soda. This is an empty can. This is way more heavier, so I can drop in. I heard one sound. I'm not cheating. You guys see it is not empty, it's full. I'm not cheating. So it seems like the mass doesn't affect the time it takes to drop down. So I'm going to show you an even more serious experiment, and I can take a break, and you can just sit down and relax. This is from BBC. I have to give them credit.
This is NASA's Space Power Facility in Cleveland, Ohio, and it is the world's biggest vacuum chamber. It's used to test spacecraft in the conditions of outer space, and it does that by pumping out the 30 tons of air in this chamber until there are about 2 grams left. And it's kind of got an eccentric construction, which is part of its history. It was built in the 1960s as a nuclear test facility to test nuclear propulsion systems, and that meant that they built it out of aluminium to make the radiation easier to deal with. Aluminium is not the best thing, the strongest material to build a vacuum chamber out of. So they built out a concrete skin, which is part radiation shielding and part an external pressure vessel, so that this thing can take the force that's present on the outside when it's pumped out to the conditions of outer space. Galileo's experiment was simple. He took a heavy object and a light one and dropped them at the same time to see which fell fastest. Now in this case, the feathers fell to the ground at a slower rate than the bowling ball because of air resistance. So in order to see the true nature of gravity, we have to remove the air. It takes 3 hours to pump out the 800,000 cubic feet of air from the chamber.
We dropped 2 millitor in the last 30 minutes.
But once it's complete, there's a near perfect vacuum inside.
6104 manual, 10% open. Station 1, go for drop. PCB 30-1, pressure set point at 240 psi. We are go for drop.
10, 9, 8, 7, 6, 5, 4. Cameras on. 2, 1. Release.
They came down exactly the same. Wow.
Exactly accurate cycle. Exactly the same.
Feathers don't move, nothing.
That's just brilliant. Isaac Newton would say that the ball and the feather fall because there's a force pulling them down, gravity. But Einstein imagined the scene very differently. The happiest thought of his life was this: the reason the bowling ball and the feather fall together is because they're not falling. They're standing still. There is no force acting on them at all. He reasoned that if you couldn't see the background there'd be no way of knowing that the ball and the feathers were being accelerated towards the Earth. So he concluded they weren't.
So Einstein is a famous guy, but we stick with Newton in this course. Okay? We say that gravity is a thing, it's a force in this class. So let's go back to this system again. So you see that when the feather falls down, usually there's air around it to drag it. So the feather is not so heavy compared to air, and if the speed falls down, it's smaller than just a big bowling ball. When I increase the weight of this other car, another car, so big such that I can get the weight of the other sliding block, I'm just going to do a free fall, and free falling object take the same amount of time to reach the ground, no matter how heavy it is. So instead of reaching 0 when the falling block is super heavy, the time it takes should reach a volume that's bigger than 0, and it should be a constant no matter how heavy it is. CONST stands for constant. Does that make sense? Okay. Now, so these are all the tendencies we know that can affect this system. No matter what the answer looks like, it must satisfy all these tendencies. It must agree with all these tendencies that we know without doing any calculation. So let's say some guy who took physics is showing off, and write down the answer directly, saying that the time it takes is m1 plus m2 divided by m2. You don't need to know how to get it yet, and you don't need to memorize it. It's just an example. And times 2h divided by g. G is just a constant with dimension of length divided by time squared. It has something to do with gravity, but don't worry about it right now. It's just a quantity, it's a constant number. So you see I am writing this thing in a very good way. This scary square root has no dimension because it's mass divided by mass, and no matter how many square root take, it's dimensionless. So if you check the dimension of this thing, it is just the dimension of h divided by g. H is this distance, so it has dimension of length. G has LT to the power of minus 2. Now, when you have t to the power t to a negative number, t to a negative power in the denominator, you can multiply both denominator and denominator by t squared and move it to the denominator. Does that make sense? The L just cancels, and 1 over t squared is just t squared. Does that, any question with that? Fractional? Okay, good. So, because there's this square root, the dimension of this square root will indeed be a time. So this answer passed dimensional analysis. The dimension makes sense. You can come up with other answers. Let's say some other guy says, no. The time should be m1 plus m2, not divided by m2, but m1. And there's even another guy saying that, no, there should be a m1 minus m2 in the denominator here. So all these answers have the correct dimension. You cannot just tell which one is wrong by dimensional analysis because the dimension all makes sense. But you can check their tendency. Well, first of all, when h is 0, the time should become 0. For all three of them, h is in the denominator. So if the denominator is 0, it becomes 0. So they all pass the tendency test for h. when h is super big, the denominator becomes super big and the time becomes super big. So they are all safe. Now, let's check the tendency of the mass. When M2 is so much smaller than M1, this thing, M1 plus M2 divided by M1, when M2 is very small compared to M1, it's like adding a cent to $1 million. When you add a cent to $1 million divided by $1 million, the answer is basically the same as $1 million divided by $1 million. You can neglect M2 because compared to M1 it's so much smaller. When you are adding two quantity, and one is just so much smaller than the other one, it's just like adding 1 cent to $1 million. The answer is just $1 million. It doesn't matter how much cent you add. This wiggly equate sign is approximately, it's not exactly equal, but you can just treat it as equal sign. Okay? So you see, when the folding block has a mass so much smaller than the sliding block, this thing is just 1, the square root is just 1. And the t prime goes to a finite number instead of infinity. So we know that this answer is wrong without taking any physics course. And you are teaching about it, you don't need Newtonian mechanics to know that because the tendency doesn't make sense. Okay? If you check the 1 on top of here, you will see it makes sense because in that case it's divided by M2. Let me do right here. Yeah, so all right. So here, if you are doing M1 plus M2 divided by M2, then when M2 is very small compared to M1, this thing becomes just M1 on the denominator and M2 in the denominator, which is going to be super small because you are dividing 1 cent by $1 million. No, which is super big because M1 is the big one. Okay? Right now we are taking M1 to be super big. So this thing is 1 million divided by 1 cent, which is super big and goes to infinity. So you know that t should be the correct answer, not t prime. That's tendency check. And sometimes, I know, so the most usual way we do tendency check is to just take one parameter to be 0 or infinity and see how the thing you calculate go. But sometimes you'll see a subtraction in the denominator, which is usually bad. This subtraction means that if M1 and M2 is similar, you got a 0 in the denominator, and the whole thing is slow. Divided by something really small gives you a really big number. But this shouldn't happen. There's nothing special about having the two trucks have the same mass. These two have the same mass, and the time it takes for it to drop down is fast, but it's not like infinity or whatever, something special. So when you see that there is a possibility to get 0 in the denominator, is the usual reason is that you forget